Welcome to the next lecture on wireless communications. Today we will talk about various coding techniques for mobile communication. First, a brief outline for today's talk. We will first summarize what we have learnt so far, followed by a study of the Galois field. We will then move over to an interesting domain of cyclic codes, which happens to be a subclass of linear block codes. And finally, we will talk about the BCH codes. In the previous lecture, we talked about linear block codes. We realized that linear block codes or LBCs have a fixed block length n, and you can have a generator matrix to generate the entire set of code words. We then visited briefly Galois field and had a very short introduction to cyclic codes. Now, let us refresh our memories about the Galois field theory. We know that a field F is a set of elements with two operations, addition and multiplication, and the elements satisfy the following 8 properties. First of all, F is closed under summation and multiplication, that is A plus B and A into B are contained in the set. Also, for all A, B and C within F, the commutative law, the associative law and the distributive law holds good, which is A plus B is equal to B plus A plus B parenthesis closed plus C is equal to A plus parenthesis B plus C are equal, and the distributive law A times B plus C is A times B plus A times C. These must hold. Further, two interesting identity elements exist. One is A plus 0, the 0 should give back A, and A times 1 should give back A. Also, there exists an additive inverse and a multiplicative inverse if we are to talk about a field. If the last property does not hold for the elements, that is, there is not the presence of a multiplicative inverse, but only an additive inverse, we called it a ring. If only the first 7 properties are satisfied, it is called a ring, otherwise it is a field. Now, we learnt last time that the objective of error control coding is to add redundancies in a known manner. In a known manner such that there is enough structure, algebraic structure within the code, and whenever there is an error, this structure breaks, and if we are smart enough, we should be able to detect an error and hopefully reconstruct it back. So, that is the whole idea of adding structures. Cyclic code is one step forward. It is a subclass of linear block code, that it has one additional requirement, an additional constraint, an additional structural requirement. What is that? A code C is cyclic if C is a linear code, and on top of that any cyclic shift of a code word is also a code word. So, if A0, A1 so and so forth till AN minus 1 forms the elements of a code word, then any cyclic rotation is, so if you put AN minus 1 before like this, and then A0, A1 up to AN minus 2, this itself is also a valid code word if it is a cyclic code. Here is an example of a binary cyclic code. Here, if you can see all of the elements, if you rotate them to the left or to the right, you end up with another valid code word. Please note, this is another example of a linear block code, but here it is not a cyclic code. The two properties of a linear block code are the all 0 code word must exist as a valid code word, and sum of any two code words is also a valid code word. On top of that, any cyclic rotation of a code word gives you another valid code word. That makes it a cyclic code. Now, let us take a brief mathematical detour and get into the domain of polynomials, because we will learn that it is very easy and logical to express a code word, which is a cyclic code word, as a polynomial. there is a one-to-one correspondence. So, what is a polynomial? A polynomial is a mathematical expression. It can be denoted as follows, and the symbol x is called the indeterminate, and the coefficients f0, f1 up to fm are the elements of any GFQ, a Galois field. So, we can define a polynomial over a field. It depends from what are you taking the coefficients from. If it is a binary polynomial, then GF2 is in question, and then you have f0, f1 etc. either a 0 or a 1. If it is GF3, then your fi's can be 0, 1 and 2. If fm, the coefficient of the highest power, is not 0, then m is called the degree of the polynomial. It is denoted by degree fx. A polynomial is called monic if its leading coefficient is unity. So, here is a polynomial over GF8. So, you can see the coefficients can take values from 0, 1, 2 up to 7, but the highest power x raised to the power 6 has a coefficient unity, hence this is a monic polynomial of degree 6. Now, let us have some definitions. Now, let us explore the properties of fx, which makes this f capital X square bracket x divided by fx a field. So, what is this capital F square bracket x? This is a set of polynomials, and if you divide it by fx, then you are doing a modulo operation, that is, whatever is the remainder after you divide any element, any symbol within this by fx, you are left with a remainder, and we are talking about that set. What we are interested in finding out is the properties of fx, which makes this thing a field, that is, it satisfies the 8 properties of a Galois field. We will shortly find out that the polynomial fx must be irreducible, which is the polynomial version of non-factorizable, that is, you cannot represent it as the multiplication of 2 other polynomials. So, a polynomial fx in capital Fx is said to be reducible if fx is ax times bx, where both ax and bx are elements of fx, and degree ax and degree bx are both smaller than degree fx. This does not hold, then it is called irreducible. A monic irreducible polynomial of degree at least 1 is called a prime polynomial. We will use this definition many times. Now, continuing with our mathematical detour, the ring fx over fx is a field if and only if fx is a prime polynomial in fx. So, we are trying to find out when will this set be a field, and the claim is this will only happen if and only if small fx is a prime polynomial. So, if this is true, we have an elegant mechanism of generating Galois fields. If we can identify a prime polynomial of degree n over GFQ, we can construct a Galois field with q raised to the power n elements. Such a field will have polynomials as the elements of the field. These polynomials will be defined over GFQ and consist of all polynomials of degree less than n. See, we are talking about taking modulo f of x, small f of x has highest power n, right. So, you can have the coefficients f0, f1, f2 up to fn minus 1, and all the polynomials that will remain if you perform this operation, right, will have the degree less than n, but there will be n coefficients. Now, each of the coefficients can take value as one of the q elements of the Galois field. So, there will be q raised to the power n such polynomials. So, let us denote capital F x over f x as a set of polynomials in f x of degree less than the degree f x with addition and multiplication carried out modulo f x. So, you divide it and whatever be the remainder is the element. Now, if a x and b x belong to capital F x by f x, then the sum a x plus b x in f x by f x is the same as in f x. This is because we have already put the degree of a x is less than f x and degree of b x is also less than f x. Carrying on this philosophy, the product a x times b x is the unique polynomial of degree less than degree f x, to which a x times b x multiplication is carried out in f x is congruent modulo f x. So, f x capital F x over f x is called the ring of polynomials over f x below f x. So, what are we looking at? This capital F x over f x is a set of polynomials, all of which have degree less than that of degree of f x, because it is the remainder after you carry out the division. And we are talking about when will this set form a ring and when will it form a field. As mentioned earlier, a ring satisfies the first 7 of the 8 axioms that define a field. A ring in which every element also has a multiplicative inverse forms a field. So, now after this brief mathematical detour, let us go back to cyclic codes and see how this arithmetic with polynomials can help us construct cyclic codes. Now, let us fix for a change R f x, the polynomial with which we divide, as x raised by n minus 1. This is very interesting, as we will soon see. And we also denote, if your small f x is x raised by n minus 1, then the set capital F x divided by f x by R n. Let us make the following observation. X n is 1 provided you are taking it modulo x n minus 1. So, x n is unity in R n. Fine. So, the modulo x n minus 1 can be reduced simply by replacing x n by 1, x n plus 1 by x, and so on and so forth. A code word can be uniquely represented by a polynomial. This is the most important observation on this slide. A code word consists of a sequence of elements and they can correspond 1 to 1 to the coefficients of the polynomial. So, we can use a polynomial to represent the locations and the values of all the elements in the code word. So, if my code word has a block length n, then there are n elements in a code word. So, we can use these elements of the code word as coefficients of a polynomial. So, a polynomial has a unique code word and a code word can be uniquely represented by a polynomial. So, for example, the code word C1, C2 up to Cn can be represented by the polynomial C0 plus C1x plus C2x square up to Cn. So, there is a 1 to 1 correspondence. Code word C0, C1, C2 can be represented like this. The C0 is missing. Another example of the code word over GF8, let us say is 207735. Then we have 27735, because the 0 is missing because it is 0 times x. So, that is missing. So, you can uniquely represent any code word as a polynomial. Now, what is interesting is multiplying any polynomial by x raises the power of each of this x by 1, and hence it represents a single right cyclic shift. So, shifting the elements, rotating them by 1 is very simple. It is just multiplying the polynomial representation of the code word by x. If you multiply it again, you shift it one more time, and so on and so forth. The only problem is that my block length of any code word is fixed and is n. if I keep on multiplying, the power of x increases. If it goes beyond x raised to the power n, then I am actually elongating my code word. I cannot. In fact, I must have a way to put the maximum power back to here. I must do a modulo operation, and this operation of putting the highest power which exceeds the block length back to the first place is done by modulo xn minus 1. So, as long as you keep on multiplying by x, but finally take modulo xn minus 1, you restrict the block length to n, and at the same time you perform the proper cyclic shifts. So, please note, if you multiply Cx by x, you raise the power by 1, but I need some way to put the Cn back before C0, because this is clearly a representation of a code word which is longer than block length n. So, we need to put this back here, and this is done by modulo xn minus 1. Hence, the importance of modulo fx. Now, here is a theorem. A code C in Rn, we know, is when you take modulo xn minus 1, is a cyclic code if and only if C satisfies the following condition: Ax and Bx, if they are elements in C, then Ax plus Bx is an element in C, it is a linearity condition, and Ax element of C, Rx element of Rn, then Ax Rx is an element of C. So, here is a brief proof for this one, and the basic philosophy here is that if you have a cyclic code, right, it can be simply represented in Rn. So, the cyclic code will have polynomials contained in fx over small fx, where small fx is xn minus 1, and it will satisfy these following two properties. It is easy to prove these two here. Now, let us move over to a method for generating cyclic codes, because all these mathematical tools are going to help us generate cyclic codes. So, first take a polynomial fx in Rn. Obtain a set of polynomials simply by multiplying fx by all possible polynomials in Rn. So, when you multiply fx by any other polynomial, you do two things. You can multiply with something x raised to the power something that will do a cyclic shift, and then add it up, which means that you are taking one code word and adding with another valid code word. The set of polynomials obtained above correspond to the set of code words belonging to a cyclic code. The block length of the code is n. So, let us take a very simple exercise. If fx is a polynomial in Rn, then if you multiply this by x plus 1, which is a valid polynomial, it tantamounts to first multiplying fx by x, which is again a valid polynomial, and then adding it to fx, which is multiplying fx with 1, which is also a valid polynomial, and together the addition should also be a valid code word in Rn. Hence, we satisfy the definition of a cyclic code, and this can be generalized for any complex polynomial within Rn. So, let C be a n comma k non-zero cyclic code in Rn. Then there exists a unique monic polynomial g of x of the smallest degree in C. This is a special polynomial. The cyclic code C consists of all multiples of the generator polynomial gx. So, we call this as the generator polynomial. It is the analog of the generator matrix. This has the capability to generate all the other valid cyclic code words. So, the cyclic code C consists of all multiples of the generator polynomial Gx by polynomials of degree k minus 1 or less, and most importantly Gx is a factor of xn minus 1. So, this is the most important fact. If this is true, then we have a very elegant and simple way to find out a generator polynomial simply by factorizing x raised to the power n minus 1. In fact, this will be one of our preferred ways to find Gx for cyclic codes. Factorize x raised to the power n minus 1. All we have to do is to factorize this quantity into irreducible monic polynomials. So, these are the conditions required for g of x. We also can find all possible cyclic code words of block length n simply by factorizing x n minus 1. Note, a cyclic code C may contain polynomials other than the generator polynomials, which will also generate C. However, the polynomial with the minimum degree is called the generator polynomial, and the degree of Gx is n minus k. So, let us see how we can encode using generator polynomial. Please note, the generator polynomial itself is a valid code word, right? Because if you multiply it with unity, you get a polynomial Gx, which should be also a valid code word. A simple encoding rule to generate the code words from the generator polynomial is as follows. Cx, which is a code word polynomial, we have established before a one-to-one correspondence between a polynomial and a word. So, Cx be the code word polynomial, Ix be the information word, and Gx be the generator polynomial. So, if you multiply Ix with Gx, you would get a valid code word polynomial. The error vector can also be represented as the error polynomial E of x. It should show at what location what is the magnitude of the error. Thus, the received word at the receiver after passing through a noisy channel can simply be expressed as the received word V of x is equal to Cx, the code word polynomial, plus the error polynomial E of x. Now, let us maintain the analogy. So, we had a generator matrix, the generator polynomial, we have a syndrome, we have a syndrome polynomial also. So, the syndrome polynomial S of x is the remainder of Vx under the division by g of x. Clearly, if g of x completely divides c of x, that is the remainder is 0, then you have a valid polynomial. Whatever be the residue, that is the remainder after dividing by g of x, is the syndrome polynomial. Please note, S of x is the remainder if you divide by g of x, what? V of x, which is nothing but remainder when you divide by g of x. What is V of x? Nothing but Cx plus Ex, and then by simple rule you can separate them out, but C of x when divided by g of x should be 0 by definition, because Gx is a multiple of Gx times Ix is C of x. So, what you get is the remainder of E of x when you divide it by g of x. Thankfully, the syndrome depends only on the error polynomial as it should, and has nothing to do with the code word polynomial. Just as a syndrome or a symptom of a disease tells about the disease, similarly the syndrome polynomial should tell us what kind of an error you have encountered. If you have a one-to-one mapping for every error pattern, a unique syndrome, then it is very easy to map back. So, it is also possible to have a matrix description of cyclic codes simply because it is a subclass of linear block code and must have a generator matrix. But the generator matrix is very easy to represent once you have the generator polynomial, and you have the generator polynomial, which is very easy once you can factorize x raised to the power n minus 1. N is your block length. So, if I give you a block length, you can immediately take x raised to the power n minus 1, factorize it, get g of x as the polynomial which can generate all the valid code words. Once you have g of x, you can have a generator matrix, which is simply written as the shifted coefficients of g of x in the various rows. It is again a k by n matrix for an n comma k code. There is a one-to-one correspondence here. If you have g of x, you can write the generator matrix. Now, just like we have a parity check matrix, we have a parity check polynomials for a valid cyclic code. What should it do? Well, if you multiply it with a valid code word, you should get a 0, and otherwise you should get a non-zero syndrome of sorts. So, we already know that g of x is a factor of x n minus 1. Hence, you can write x n minus 1 is equal to h of x times g of x. It is a factor after all. Now, h of x is some polynomial, it is kind of a dual. So, the following can be concluded simply by observing the above equation. Since g x is monic, h x has to be monic, because x raised to the power n is the highest coefficient is 1. But please note, here we are not talking only of binary cyclic codes. This is valid for all Galois fields. So, even if I am talking about cyclic codes over GF8, GF16, this will still hold good, right. But g of x must be monic, that is the highest coefficient should have a coefficient equal to 1, the highest power of x. So, since gx is monic, hx has to be monic, because the left hand side of the equation is also monic. Since the degree of g of x is n minus k, the degree of gx must be, the degree of hx must be k. Suppose C is a cyclic code in Rn with generator polynomial g of x. Recall that we are denoting fx by small fx by Rn, where fx is x raised to the power n minus 1. Then any code word belonging to C can be written as Cx is equal to Ax times g of x. We have noted this before, where the polynomial a of x is within Rn. Therefore, within Rn, Cx times h of x is equal to Ax gx h of x, but for every valid gx and hx, it should be 0. So, it is 0. So, that means if you multiply Cx with hx, you end up with a 0. Just like the parity check matrix, when multiplied with the code word vector, you end up with a 0 vector. If you multiply the parity check polynomial with a valid code word polynomial, you end up with the 0 polynomial. Okay. Had there been an error, you will get a non-zero polynomial here, and that will form your error polynomial. So, let us look at an example. For binary codes of block length n is equal to 7, we have x raised to the power n minus 1 equal to x raised to the power 7 minus 1. And the first step always in the search of cyclic codes is to factorize this. In a previous lecture, we had looked at certain factorizing techniques. So, the first step is simple. X raised to the power 7 minus 1 is x raised to the power x minus 1 times x raised to the power 6 plus x raised to the power 5, and so on and so forth up to x raised to the power 0, which can be further factorized into these two terms. So, we have done the factorization, and all of them are irreducible. They cannot be factorized further, which means the three of them and any product thereof can form a valid generator polynomial. It has to be a factor of x raised to the power 7 minus 1. So, just consider x cubed plus x plus 1. Since Gx is a factor of x raised to 7 minus 1, there is a cyclic code that can be generated by it. Now, having found out a generator polynomial, which in our case here is x cubed plus x plus 1, I can simply write the generator matrix by using the coefficients 1, 1, 0, 1 are the first 3 coefficients in the decreasing order, because the coefficients of x squared is 0 here, which is reflected here. So, x 0, x 1, x 2 and x 3, and then a cyclic shifted version, another one and another one. The number of rows is 4, the number of columns is 7, n is equal to 7 and k is equal to 4, and n minus k is the highest power of x here. If you know G, you can also find out the parity check matrix. So, this is nothing but whatever is remaining. So, if you multiply x minus 1 with x cube plus x square plus 1, you get this one, and this corresponds to the coefficients of the parity check matrix. The number of rows is n minus k is equal to 3, the number of columns is equal to n is equal to 7. So, this is the G and the H matrix for your cyclic code. Please note, here we have a recipe to make as many generator polynomials as possible. In fact, 1, 2, 3 are clearly visible, then product of these two 4, product of these two 5, product of these two 6, and then there are 2 more factors for x raised to the power 7 minus 1. One is unity, it is also a factor, and itself x raised to the power 7 minus 1, that is also a factor of x raised to the power 7 minus 1. So, you have 8 possible generator polynomials out of x raised to the power 7 minus 1. Question.
So in hx we can consider anything like x minus 1, so we can take also x square plus x plus 1.
Question is being asked about hx. Hx, as we know, has a very interesting property. We have denoted hx times gx is equal to x raised to the power n minus 1. So, if I choose my generator polynomial for an instance as x cubed plus x plus 1, then whatever are the other 2 terms left, their product is h of x. Had I chosen my generator polynomial as x squared, x cubed plus x squared plus 1, it is also a valid generator polynomial, because it is a factor, it is monic, it is a factor of x raised to the power 7 minus 1. In that case, the product of x minus 1 and x cubed plus x plus 1, the first 2 terms, would have been h of x. Okay. So, g of x times h of x is x raised to n minus 1. So, after the effort that we put in to figure out factorization of polynomial, it is now a piece of cake to figure out how to get to the various kinds of generator polynomials. In fact, once you factorize, you found out all possible generator polynomials for the block length 7, because I factorized x raised to the 7 minus 1 once. In fact, I have not 1, not 2, but the existence of 8 possible cyclic codes here. Of course, some of them are trivial. So, the minimum distance of this code is 3, and if you observe it carefully, this happens to be the 7, 4 Hamming code. So, the Hamming code, which is also a perfect code, also happens to be a cyclic code, a very versatile code. Now, let us give a flavor to this error control coding from the perspective of mobile communications. In mobile communications, we have already encountered that the wireless channel is a very hostile channel. It goes through deep fades, and whenever we pass through a fade, we have a burst of errors. It depends upon the fade duration. If the fade duration is large, then we have several bits wiped out at a time, and these are consecutive bits. So far, the philosophy of error control coding has been that we can handle random errors. But if the errors start happening in bursts, that is, all the errors are situated next to each other, then we are in problem. Then we must devise some smart techniques to overcome the burst errors. As we will see, cyclic codes are phenomenally good in overcoming burst errors. In many real life channels, as we know, in wireless channels, errors are not random, but occur in bursts. For example, the mobile radio channel. When errors occur at a stretch as opposed to random errors, we call them burst errors. A cyclic burst of length t is a vector whose non-zero components are among the t successive components, but note the first and the last of which are non-zero. So, if you say it is a burst of length t, then the first and the last elements in the error pattern should not be 0. Let us take a small example. Let the transmitted sequence of bits transmitted at 10 kilobits per second over a wireless channel be followed. Suppose after 0.5 millisecond of the start of transmission, the channel experiences a fade of duration 1 millisecond. Now, we have already devised mathematical tools to predict the average duration of fade. Let this be a measured quantity, 1 millisecond. So, during this time interval, the channel corrupts all the transmitted bits. So, here is a start of fade, and the fade lasts for so long, and then the fade ends, because we know that the data rate and we also know how long the fade lasts. Here this is kind of an error pattern. So, all the bits within this fade have been flipped, but clearly we do not know the fact that all of them have been flipped. If we knew it, we will just flip it back and a problem is solved. So, fade does not mean that all the bits are exactly flipped. In fact, we do not know whether the bit is flipped or not, but there is a possibility of being flipped. But most importantly, for the burst of length t, the first and the last should not be 0, rest all can be zeros. So, it could have been 1, 0, 0, 0, 0, 0, 0 up to here and then 1 again, it will still qualify as a burst of length t. So, this is an example of a burst error where a portion of the transmitted sequence gets garbled due to the channel. Here the length of the burst is 10 bits. So, let us look at an example. For a binary code of block length n is equal to 15, consider the generator polynomial like this. So, generator polynomial gives you a lot of information. You only know n is equal to 15, but you know that the highest power 6 corresponds to n minus k, right. So, n minus k is 6. So, you can find out k from here, and then you can find out the code rate. This code is capable of correcting bursts of length 3 or less. To prove this, we must show that all syndromes corresponding to the different burst errors are distinct. So, the different bursts are burst of length 1, it is just saying that one bit occurs at any one of the 15 locations. What are the 15 locations? 0 through 14. So, Ex, which is our polynomial for burst error, is x raised to power I. Burst of length 2 can be denoted by Ex is equal to x raised to power I 1 plus x, because they have to be 2 consecutive bits which are in error. It is a burst of length 2. Okay. Burst of length 3 can be denoted as follows. They have to be 3 consecutive errors. It can be shown that the syndrome of all these 56 possibilities. So, there are only 56 possible burst lengths of burst length 1, 2 or 3. So, if I say this code can correct all burst errors of up to length 3, then all the possible error patterns, all the possible burst error patterns must have a unique syndrome polynomial. How do we find out the syndrome polynomial? Well, It is take this E of x divided by g of x, the whatever is the remainder is the syndrome polynomial. So, it can be shown that for all these cases, if you take it modulo g of x, you come up with unique polynomials. If we have unique polynomials, you can map it back and hence correct all errors of burst length 3 or less. A table can be made for each pattern and the corresponding syndrome which can be used for correcting a burst error of length 3 or less can be found out. Let us look at another example, a code which is good at correcting burst errors. It is called the FIRE codes. A FIRE code is a cyclic burst error correcting code over GFQ with a generator polynomial given as Gx is equal to x raised to the power 2t minus 1 times p of x, where px is a prime polynomial over GFQ whose degree m is not smaller than t, and px does not divide x raised to the power 2t minus 1 minus 1. So, under this constraint, whatever code you form is called a FIRE code. It has some very interesting properties. The block length of the FIRE code is the smallest integer n such that Gx divides x raised to the n minus 1. Okay. A FIRE code can correct all burst errors of length t or less. So, within the definition of your generator polynomial, I have put in how many burst errors can I correct. So, I have a design rule here. I fit in a value of t. If it is 3, you have x raised to the power 2 into 3 6 minus 1 5 x raised to the power 5 minus 1 times p of x, where p of x must satisfy this property. P of x does not divide x raised to the power 5 minus 1. What is interesting is FIRE codes become more efficient as we increase t. What does it mean? Efficiency in terms of the code rate. So, if you increase this t, right, you have on the y axis the code rate, and how do you get the code rate from here? Well, n minus k is the highest part of this whole thing. So, as you increase your t on the x axis, the code rate tends to go up, but your block length also tends to go up. So, FIRE codes of large block lengths are very useful. Let us now peek briefly into a subclass of cyclic codes, which is the Bose-Chaudhary-Hockingham codes, or more popularly known as the BCH codes. So, the BCH codes are a subclass of cyclic codes, which are a subclass of linear block codes. The class of BCH codes is one of the most powerful known class of linear cyclic block codes. The BCH codes are known for their multiple error correcting capabilities and the ease of decoding and encoding. Now, there is also a paradigm shift. So far, our approach has been to construct a code and then find out its minimum distance. The BCH code tells you, please tell me how much is the desired minimum distance of the code, and it will design a code accordingly. So, it is the other way around. So far, we make a code, we construct a code and then find the minimum distance, and we talk about how many errors it can correct. If you go the other way around, it tells you and it asks for the parameter how many errors is required to be corrected by the code, and then constructs a code accordingly. So, in this case, we start at the other end. Now, the class of BCH codes were discovered independently by Hockingham in 59 and Bose-Raychaudhuri in 60, and hence the name BCH. The Reed-Solomon codes are a subclass of BCH codes, but an important subclass with a wide range of applications in digital signal processing, digital communications and data storage. The Reed-Solomon codes were discovered by Reed and Solomon, who published a 5-page paper in the Journal of Society of Industrial and Applied Mathematics in 60. Despite their advantages, RS codes, the Reed-Solomon codes, did not go into use immediately after the invention. Why? They had to wait for the hardware technology to catch up at that time. So today, the very popular RS codes which we find in our CD, the audio CDs, the video CDs, even for deep space exploration and lot of wireless communication devices, could not be put into immediate use because the required technology was not there. So in 60s, there was no such thing as fast digital electronics, not by today's standard. So we will summarize today's talk here. We started off by looking at the Galois field, followed by a detailed understanding of cyclic codes. We came up with an interesting polynomial representation of cyclic codes. We realized that there is a one-to-one correspondence between polynomials and cyclic codes. What was interesting is that if you multiply a polynomial by x, you right shift the code word elements, and what is important is for cyclic codes, any shift, any cyclic shift of the code words is also a valid code word. Then we realize that there is a notion of a generator polynomial in cyclic codes, and then the analogy does not stop there. You have a syndrome polynomial and as a parity check polynomial. We also realize the importance that you have to take modulo x raised by n minus 1, so that when you multiply gx by any valid polynomial, you do not overshoot the block length. Then we also realize that gx, the generator polynomial, must be a factor of x raised by n minus 1. Thereby, we figured out a way to come up with all possible valid cyclic code words of a certain block length n. All we have to do is take x raised by n minus 1 and factorize it, and in front of our eyes we will have all the possible valid generator polynomials. We then moved over to the domain of burst error correction. We realized that in mobile environments where we encounter deep fades, we tend to lose not random bits, but also bits which are in burst errors. So we lose a sequence of bits. Our regular error control techniques are incapable of overcoming burst errors. We have to have special kind of codes for that. We looked at certain cyclic codes which are known to be good burst error correcting codes. One of the most important one is the fire codes. We then briefly had a peek at the BCH codes, which form an important subclass of cyclic codes, not only because you can very easily encode and decode them, but also that you can have a constructive strategy for BCH codes. At this moment in time, please note that cyclic codes, BCH codes and Reed-Solomon codes, which is a subclass of BCH codes, though non-binary, all are from the linear block codes. They are all subsets of the linear block codes. So all the techniques that we have learned and developed for linear block codes are also valid for cyclic codes, your BCH codes and Reed-Solomon codes. However, in the subsequent lectures, we will look at efficient encoding decoding strategies for Reed-Solomon and BCH codes as well. So this is a nice place to conclude our lecture, and we will look at BCH codes starting from the next class.